This concept of slope. Who could tell me, just from their basic knowledge of math and their previous courses, what exactly is slope? What is slope? Rise over run. And that's the definition that we know of it as, is rise over run. Rise meaning what? What does rise really mean? How far it goes up. And run means?
How far to the left or right.
Yeah, to the left or right. So rise over run is the traditional definition, which is fine. And we're going to utilize that concept. So let's go into the next part here. And we're seeing here the simple example of slope. Slope is easily computed with triangles, right? Any right triangle, the hypotenuse itself increases or decreases at some angle or some slope. So if I look at the hypotenuse here of this triangle, the hypotenuse is like my linear function. This is the run, this is the rise, the slope is the actual steepness of the line. As a line, so take a look so you can see this. As a line goes from here to here, what happens to slope? From here to here, what happens to slope? It increases. So positive slope means it's getting steeper. But what happens when it passes the vertical position? It goes over here now. It's negative slope. So negative slope is a function that would be like downhill, right? Decreasing. And we always look mathematically from left to right. It's just the way it just makes sense, right? The way you've been taught. If x is negative over here and x is positive over here, we start over here and we count up. So when we look at this figure from left to right, we see that this is a rise, right? Or it's an increasing function. It goes up. So this slope here has to be positive. Again, this goes up, this goes to the right. If we think about this in terms of our equations and our coordinates here, I'd rather you also consider this. So rise and run are good words for this, but I want you to start remembering delta y over delta x. The reason I say delta is because delta infers change. In your later courses, you're going to use the symbol delta a lot. In physics and calculus both, you're going to see delta appear over and over. Delta means change. Change means final minus initial. So the final point here is x2, y2. The initial point here is x1, y1. Well, how do I find the run? I think about how far this is apart. Okay, so if I want to do that, let me point on here so you can see it later. If I want to figure out this distance from here to here, all I need to do is consider the fact that I continue this down the whole way. So if I wanted to see this visually, just continue it down to the axis. And then look at your x-axis. This is the value x1 right here. This is the value x2. How would I find the distance between 2 points? I take the larger one minus the smaller one, thus x2 minus x1. I can do the exact same thing along the y-axis. I could take this coordinate, extend it to the y-axis, extend this one to the y-axis. This is y2, this is y1. How do I find that height between y1 and y2? I take the larger number, y2, minus the smaller number, y1, and there's my definition for rise. So, although you're using rise over run, let's use this, please. Let's use this formula throughout the year. Okay, let's recognize that formula, delta y over delta x. Delta y over delta x. All right, with that said, let's classify slope. So already I asked the question about positive and negative, and you saw that, and you can see that on the far right. But the one on the left is the one that most students not have trouble with, but confuse all the time. Here's how I want you to think about it. All right? Ready? If I'm walking uphill, right? If I'm walking uphill and there's a given slope, that slope is really telling me for every movement up, I have to move a certain distance laterally. So if I'm literally climbing a mountain, every time I go up, I have to go over. I have to go up, I have to go over. So when slope is positive, think about climbing something. When slope is positive, because it's a positive incline. When slope is negative, think about going downhill. You're like losing energy. It's a decreasing function. I'm trying to relate it to like physics and tangible things. But zero slope, it means simply that I don't have to go up or down every time I move over. That's what the ground is. The ground slope should be zero. It should be, right? Obviously, it's not always true. And you can tell if you put like a marble down, never see a marble, put a marble down, it just rolls on its own. It means that whatever you're situated on is not actually flat. If you look at like old apartments in New York City, a lot of them over time, what happens is the floorboards start to bend. It's called creep. Over time, they start to actually bend and bow in different areas. So I used to live, prior to moving into New York City, I lived in my grandma's old house in Brooklyn that was built in like 1920. It used to actually have the first floor was a house, was like a garage for a carriage. It was called a carriage house. You would actually park your carriage on the first floor. They remodeled it for a while, but the second and third floor never got redone. And I used to live on the second floor, and literally, this is no joke. Like, I would sit in like a desk chair, like a wheelie chair, and I would just start sliding down because there was a little bit of a negative slope. So over time, eventually, what I did was I actually I leveled it myself. I put a carpet over it, and I put like a little piece of wood that was cut at the right angle, so that when I sat in my chair, I was actually sitting on flat ground. Because it just got annoying, there were no locks on it. It was a nice chair. But again, because of slope. If there's no slope, there's no possibility to lose or gain energy. That's what you're really thinking about with slope. This is gaining energy by going up slope. This is losing energy, but moving left to right, I'm not changing my height. So my energy, in this case really it's potential energy, is not really changing. Why does the other one say slope is undefined? Because undefined is the thing you always learn about. And it makes sense, it'll work.
Isn't it undefined when zeros on the bottom because you can't look at zero?
Yeah, and that's the reason here. Because if I look at this slope right here, right, let's start with zero slope. I look at 2 points. Connect those 2 dots in red there. The rise is 0. The run is whatever distance that is. So if I wanted the slope of this first line, I had the slope is the rise is 0, the run is some number, so the slope turns out to be 0. But in blue, look at the 2 blue dots now. If I look at the blue dots, what I see is that the rise is some number. It's rising up. But is it moving left to right? Is there any run in that line? No run. So as Alex mentioned here, oops, I'll put it over here. We have some rise, but no run. And in math, we talk about the fact that you can't divide by 0. We say that it's undefined, undefined. And you're going to learn later in pre-calculus and calculus that there's something called a limit. And the idea is really that this limit approaches infinity. And the way to think about it, and I'll explain this, it's not really actually difficult to explain. Imagine if I had, here we go. I got this box of weights, okay? And in this box of weights, I'm just going to tell you. Let's say there's 30 weights in here. Okay? There's 30 weights in here. If I take 2 out at a time, how many times do I have to do this? It's 30 weights, I take 2 at a time. 15 times, right? Okay. Instead of taking 2 at a time, now I take 3 out at a time. How many times does that have to happen? 10 times. Okay. What if instead of taking 1 or 2 out at a time, I tried to take out like little pieces at a time, like a half at a time? Or if I could cut it in half hypothetically. Take a half out at a time, there's 30 of these. How many times do I have to take a half out to take out a total of 30? 60 times. So what I'm noticing is that if I divide by a smaller number like a half, the value of the fraction goes up dramatically. What if I take out 0 at a time? How many times do I have to do this? I take out none every time. How long will it take me to physically have this happen? Forever, right? It's never gonna work because I'm taking none out. What is forever? What does that really mean? Forever means as time goes on forever and ever. So what's a number that goes on forever and ever? Yeah, it's really infinite. You're approaching infinity is what you're doing here. So in this problem here, when we're looking at the slope of a vertical line, we can say that there is no slope, or slope is undefined here. But in reality here, I want you to start to think about this, and you're going to use this in your math course a little bit later. Think about this as an approaching infinity slope. And it makes sense, actually. Let me explain, because a minute ago you guys gave me an answer that would have actually alluded to this. What's the slope of this line right here? In general, everybody, what's the slope of this line, flat line? Okay, it's getting more and more what? So it's getting more and more positive. So give me a slope here, hypothetically. What could the slope be? Okay, 4. I go a little bit higher. 7, 8, 9, right? Okay, but eventually I get to this vertical part, and then it becomes negative on this side, right? But isn't my slope increasing as I keep doing this? So what is the largest number you can increase to? That's the concept of infinity. So the slope is really infinite when it's a vertical line, or it approaches infinity, the limit of that value. So when we're looking at slope, I want you to recognize here that this slope is actually equal to 0. And this slope up here, we say is actually undefined. Some books actually call it no slope, and that's what I'm writing over here. Okay, so undefined or no slope, these are the same things. This is also the same thing as saying that the slope is infinite. Very different than saying a slope of 0. No slope is different than 0 slope. And that sounds like it's ridiculous because if I said to you, how many dollars do you have? And you said, I have $0. It'd be the same thing as saying, I have no dollars, I have no money. So no money and $0 is the same thing in your mind, right? 0 and saying I have none of something. But when we say there is no slope, literally, we mean that the slope is undefined or the slope is actually infinite. Okay, those are all interchangeable. Those circle things and this. But horizontal lines have 0 slope. These 3 are really easy, just practice problems. So let's quickly go through these. Okay, try to blow through question A and B right away. C might be a little bit trickier, but A and B should be really nice and quick. Just don't alter it at all. Throw it right in there and don't change it. What do we get for these slopes here? Just so you know, it's as soon as it crosses the plane. So as soon as the front weight goes over that edge, is when the timer stops. So it would have stopped at like 11 actually, just so you know. So keep that in mind. Okay? 'Cause a couple groups today were like, oh, it didn't fall off. Remember, it's when it breaks the plane is when it stops counting. Consider where you're starting it, how high up and stuff. Check your answer for A. If you have A right, you're probably going to get the rest of them right? It's pretty obvious. If you can get one of each, you can do the rest of them. Yeah.
For if something's undefined, so it's like this, can you say undefined or infinite?
Yeah, that's fine. If you actually are writing the slope out and you say it as infinite slope or undefined slope, I'll accept both of those. Check my work. Make sure I'm doing it right too, please. Okay, but that's the first 2 that I got here. Okay, and that's the third one right there. It should be really easy, right? Can we go on to the next thing? Yeah? We've seen slope before. We've calculated slope at some point in time. So this next part, this is a little bit trickier. So this is something that actually, I never learned this in high school. I never learned that there's a shortcut to get slope when it's in standard form. And if you don't really want to use it, you really don't have to use it. You don't have to use this shortcut I'm going to show you. But it turns out that if something is ever written in standard form, right, which is given at the top here, this is standard form right here. If something is ever written in standard form and you want to find the slope, you could just use this value right here. And it will always work. Okay, it will always work. The reason you can do that is because if you just look at this equation and solve it for y, it works. Try and solve that equation for y. So move ax over. You get by equals c minus ax. Divide by b. You get c over b minus a over b times x. And take a look at the equation now. And I know we didn't do slope-intercept yet, but for those of you I know that all know this form, the y-intercept would be c over b, right? C over b would be the y-intercept, and the slope would be negative a over b. So it's very useful to utilize this concept of negative a over b being the slope in standard form if you don't want to have to resolve every single time. So if it's in standard form, I don't want to have to get y by itself every time, so I can just look at a and b and get my slope right away. Okay, there's a proof to it. I've gone over this proof in the past. I do a lengthy one of it in the notes so you can see this. I don't think it's worth our time. Okay, showing you the way I showed you just now shows you alone that negative a over b right here must be the slope. If you want to see the rest of the proof, please look at my completed notes for here. Okay, I can go through it, but I honestly don't think it's worth our time right now. I'd rather get to other stuff. Okay, but again, c over b is the y-intercept, and negative a over b is the slope. C over b is the y-intercept right here. That's always the y-intercept. And this right here is the slope. So in example 2, very simply put, you're given something in standard form. Standard form tells me ax plus by equals c. So a is 2 and b is 3. And since slope equals negative a over b, this is simply going to be negative 2/3. So I wrote all that stuff down, but honestly, you could just see this and get the answer right away. Negative a over b, look at it. There's 2, 3, negative 2 over 3. That's your answer. Obviously, you could solve for y and do that and get the slope. That's totally fine also. I don't care. I really don't. This is not going to be one of those things that I'm going to say, find the slope using negative a over b. It's up to you to choose in that case. The other thing with the intercepts was really important that you use that method. Here, I don't care. Use this or just solve for y. And what I mean solve for y is solve this equation up here for y. You will literally get y equals, what is it going to be? 5 over 3 minus 2 over 3x. That's what you'll get as an equation. But if you don't want to have to solve, I think this is faster. So it's something that's useful to have. But again, I'm telling you, I never learned it in high school and didn't really need it. So if you don't want to write that fact down or don't use it, it's not a big deal. This is what's important, this kind of stuff. Let's take a look at some data analysis. Okay, the question presented here is the following. Determine if the given points listed in the table lie on a line. If they do lie on a line, give the slope of said line. Okay, if they do lie on a line, give the slope. So the first way I can do this is by honestly just drawing a quick graph of it and seeing if it's linear, right? Get an idea. That's one way to think about it visually. Remember we talked about math? There's the graphical interpretation. That's what that would be. This is a numerical interpretation. I can come up with an algebraic interpretation, and verbally I can see x is going up every time by what? I could say x goes up by 1 and y goes down by 2. So that's a constant change, isn't it? Which would indicate to me that this is changing at a constant rate, therefore is linear. Things that are linear, watch, ready? I'm going to walk across the room. 1 meter every second I'm walking. If I were to graph that on an actual graph, it would look like this. Every second I gain another meter of position. So I go 1 second, I'm at the location of 1. After 2 seconds, I'm at 2. After 3 seconds, at 3, etc., etc. So each of these little pieces together are 4 linear pieces that are connected. That's what you're seeing here. In the first set of data, that's the easiest one of them. What would the slope be for part A? What would the slope be? What's the slope? What do you got?
-2.
Yeah, because y is going down by 2 and x is going up by 1, which yields just -2. So my rise over run, you look at the y is going down by 2, so I put a -2, x is going up by 1. How about the next part? Alex, what do you got?
It's not.
It's not or it is?
It's not.
Okay, how come?
Because you have like, it's not, it like changes to like if y, the first y value is -3, then it would work. 'Cause it's
Okay.
going up,
But what are you noticing?
starting and then you're going negative, and then you're going back to positive. You can't really do that.
So this is what Alex is picking up on. Okay, he's recognizing that this is changing in values. Now, Alex, believe it or not, that doesn't tell us enough, because I can have that and this could be linear. What about the x part? Can we say that proves that it's not linear, Alex? The x part is doing what?
Going up
By?
to
Every time, right? So, hypothetically speaking, okay, I need to look at the change in both every time. So you're right, that the y value is showing us that this is not linear, this function. But this is going up by 2 every single time. Sorry, the middle one goes up by 4, I should say. Right? The middle one does go up by 4, not 2. Alright? The middle one goes up by 4 here. So if I look at this, let's see, it's going to work? No, it's still not going to work, because if I look at this, I could find the slope at every piece. Ready? Watch what I'm going to do here. Watch where I'm pointing, please. The slope between the first 2 coordinates is going to be -3 over 2. Please look up. -3 over 2. the slope between the next set of coordinates, between these coordinates here and here, is going to be 3 over 4. And then the slope between these coordinates is going to be 3 over 2. So I could find the slope between every given set of coordinates. And that's what we kind of did here. And we recognized this went up 1, down 2, up 1, down 2, up 1, down 2. So that was consistent. This was not. So part B is not. How about part C? How about part C? So write down all your deltas, please. Write down all your deltas like I did a minute ago. So I wrote down my deltas, okay? I'm looking now at the changes between them. What do I pick up on here? I don't know what the answer is, but what do I pick up on? What do you notice is happening? Look for patterns, right? Look for patterns in numbers. Again, not asking for the answer. What do I notice though? Quickly, what do I notice?
Like the y value is different than x value, and then y value is different than x value.
Yeah, look. This is double this. Double this, you get this. Double this, you get this. Right? Aren't they all doubles of each other? They also coordinated that way. So when I'm looking at slope, I think of, ready? 2 over 1. That's a slope of 2. 4 over 2. That's a slope of 2. 8 over 4. That's a slope of 2. So this has a slope of 2 for this last one. Okay, here's what I want you to do. Listen carefully. So we just finished example 3. I want to do examples 4, 5, and 6 tomorrow in class. It's going to take a little while. Tonight I'm not going to give you regular homework because that homework's not going to be due for 3 until next week. So tonight, what do you get a head start on? Or at least start continuing? Problem sets, okay? So problem sets, it's going to be what sections do we do? 4, 2, 4, 2, 5, 2, 6, 2, 7, 3, 1, 3, 2, 3, 3. And that's all due on Friday. All of that is due Friday. 2, 6 is very little. 2, 7 is actually only 8 questions in the problem set. Okay? So please space it out evenly. Do at least half tonight, at least, if not more, so you can finish up the rest tomorrow night. The homework for 3-3 won't be due until Monday. Okay, when you take the test itself. Okay. Why isn't this recording? It's the same thing with this one. Okay, here we go. This one is. Alright, the last one. You are going to use a calculator actually this time. You are going to use a calculator. So let's go ahead and plot this family of functions, okay? And here's what I want you to do. In your calculator, start with y1 equals, and let's start with 1/2 x and graph that. Now, if you have the color calculator, this could come in handy. If your calculator doesn't have color, it's not the end of the world. I'll show you how you can change the line to make it look different. I have a calculator emulator on my computer. I'll show you what it looks like. Yes?
Which is the calculator color?
What is the color one now? 84 color, is that what it's called? It's like an 84 color is the name of it. It really, it has no significant, there's no increase whatsoever in the functionality. It's just that it's in color. So if you wanted to graph several lines at once, you'll see the different colors of them. But I'm going to show you guys on my computer. I'll put my computer up in a second. I'm going to show you how to do that on the regular calculator without color. I'm like a calculator pro. So if you ever have a question on the calculator, I know like everything about these calculators. So feel free to ask me. The reason being, honestly, when I was in high school, TI-83 came out when I was in 10th grade. It was like the biggest thing. Calculators, graphing calculators at least, were not around. I know. I'm not that old, but I'm old enough. And I actually taught myself how to use the calculator, to be honest. We had a teacher who really didn't know how to use the calculator at all, and she didn't want to learn how to use it throughout the year. So me and a couple other students, we looked at, you get like a manual. Most people throw the manual out. We literally looked through the manual and learned how to teach ourselves. So I know how to use like anything on a calculator, but whatever. All I'm saying, not to brag, I'm saying it so if you want to come by and ask me questions, if you're not sure about something, come by. Okay, so here's my virtual calculator you can take a look at. So it's just 83, right? All right, so now, if I want to graph something, I click y equals in the top left. I'm going to clear what's in here. Hit clear, go down, I'm going to hit clear. Okay, I don't want anything in my calculator yet. Now, I'm going to graph the first function. The first thing I wanted you to graph, if you recall, was y equals 1/2 x. How am I going to type that in the calculator? Make believe you didn't know decimals. I know you could put 0.5x. But let's say fractions because I want you to practice. If I'm typing this in the calculator, Valentina, what should I write?
I put 1 divided by 2.
1 divided by 2. Go ahead.
X. So
X.
alpha and then,
So x is right here, by the way. X, t, theta, n is the x you're going to use for x. Helen, why isn't this going to work?
Because it's just going to give, well, the way I do it is you have to press alpha and then you press stop at y equals, so that gives you f1, and then that gives you like an option of fraction, like mixed number.
So she used the fractional thing with this like math type. You can have it on math type. But my question, so you're right, you can use math type in order to put a fraction vertically. Why would this not be correct?
It's not 1/2 x, it's like 1 over 2x.
You wrote 1 over 2x. That's what that says, 1 over 2x. Think about PEMDAS, Valentina. What does PEMDAS tell you? From multiplication and division, it goes left to right. So the calculator will do 1, it will divide it by 2, right? And then it's going to take, well actually no, will this work? Oh, this won't work actually. I'm sorry, I apologize. Because this will take 1, it'll divide it by 2, and then it'll multiply that answer by x. So this will work in this case. But all I'm saying is this. To be safe, when you're working with fractions as coefficients and equations, just put parentheses around them to be safe. Okay, but this actually would work. I apologize. Sorry, Eduardo, I led you to false belief there. That's my bad. But this would have worked. But I would have put parentheses to be safe. See what I just did, by the way? Did anybody see that? Let me do that again. This is a command that nobody seems to know. So say I'm over here, and I want to retype the whole thing, but I want to squeeze in a parentheses before the number 1. Go to the number 1, and then press second, insert. And it starts to change the cursor. See the cursor now is like that? And when I put parentheses, it automatically puts it before whatever you're on. And then if I go to the right, it changes back to the old cursor, parentheses, x. Okay? Again, these are just small commands along the way. But yes, that actually would have worked for us. I thought it would have worked. Regina.
Where's the insert button?
Second, delete. Second, delete. Okay, the delete key is also very important. It doesn't clear the whole line. If I hit clear, the whole line goes away. If I wanted to get rid of x, I could go on x and press delete, and now x is gone. Okay? Now, next piece. This is good that we're spending today doing this, so we have the rest of the period and we're not in a rush. I can teach you so much on the calculator right now. The next thing, there's so many features under Zoom. And I want to discuss what they mean because most students have no clue. So just hit Zoom, please. Don't choose any, just hit Zoom. Okay, just hit Zoom. First, I recommend that you never use Zoom in and Zoom out. Okay, it's rare that you're going to use those features. And I'll explain why in a minute when I talk about this thing called window. But the ones that you will use, the most traditional one is Zoom 6. Zoom 6 says Z standard. What does Zoom 6 do on the calculator?
It sets you back and clears the memory.
Okay, but it defaults to what? What's the default?
It's a fourth quadrant thing.
From where to where on your axis?
-10 to +10.
And?
-10 to +10.
Okay, that's the default setup on this calculator. -10 to 10, -10 to 10. It's your viewing window. So if you hit Zoom standard, it will automatically default to that. You can do it now if you want, but then go back to Zoom, please, so we can see stuff. You know?
If you do like a stat plot, you would press the stat.
Yes. Absolutely. Especially if you're using stat plots where you enter into the list, you can enter given data and use like a regression curve. You use stat plot and Zoom stat.
Is
When-
that for line plus too?
Yep. Yep, exactly. Because you can do what's called a linear regression, store that in Y1, and we're going to do an activity with that actually in the second quarter. In the second quarter because it's based on this. And then you can see the line and the data points to see how close they are. The first 5, though, honestly, I in my career as a student, teacher, graduate student in engineering, have never used 1 through 5. I don't see any, has anyone used them that finds a purpose? Because I would love to know if you have and found success. Which one have you used?
I just like zoom in or zoom out. If I hit a line, I need to find like a certain value, but then you could just go to like the chart.
Yes. Okay, so I agree with you there, Helen. Helen's right. If you want to find like an intersection of 2 lines and see exactly where it is, you can zoom in, but there are other commands that find intersections, that find maxes and mins, and we're going to go through those also. So the zoom in feature could be useful, but other things can kind of take its place. Let's keep going. So Zoom 7 is for trig. So when you're graphing sine and cosine waves, you're going to see this next year in geometry honors, the next year after that in pre-calc honors. you'll start to talk about sine and cosine waves, and it will change all of your domains and your ranges. It'll go from -4 to 4, and from -2 pi to +2 pi. That's something you haven't learned yet, so don't worry right now, but know that you will use that later on. That's zoom trig. Zoom integer, I don't even know, I've never used it. Zoom status, what Helen mentioned. If you're going to plot points, which we will use this in the second quarter, we're going to plot points and do like a line of best fit or a curve of best fit, we'll use that feature. I don't think I've ever used zoom fit. Oh, but I haven't used zoom fit, but you know what zoom fit does? It fits to the graph that you're giving it by default. So for example, let's say this is my graph. Okay? I'm looking at a parabola. We're going to look at these in the next chapter or two. What part of the graph doesn't matter? I mean, like, really, look. Like, this is all extra. The graph is not occurring in any of those regions, right? So if you hit zoom fit, it'll automatically find a window to zoom to so that the graph fits perfectly. That's an okay thing to do, but sometimes it zooms in so far that you don't even know where your axis are. You know what I'm saying? So you might not want to use this feature, especially if you're only in like one quadrant up here. Because then it's going to zoom into the window right here. And then it's like, well, where's your axis? You don't even know what things are. So I have not used zoom fit much, but I guess it could come in handy if you don't know where the graph is. You know what it's good actually here? Maybe jot this down or remember it. I know it was good. Word problems that involve a graph that's at like y equals 20,000. So let's say you're graphing revenue versus the number of items sold. And your revenue function, R, is a function of N, the number of items sold. And the revenue is $30,000. Well, that's your Y value. For how many things sold? 2,000 items sold. That's your X value. So your graph is going to be way off. If you zoom 6, it goes from -10 to 10, -10 to 10. 20,000 is way outside of -10. You're never going to find your graph. So zoom fit could be useful if you can't find your graph. If you hit zoom standard and you just literally, there's no graph showing up, maybe zoom fit would be useful to find it. Okay, so for today, let's hit zoom 6 to standardize it. And this is the graph of y equals 1/2 x. In y2 now, please, in y2, let's increase our slope to 1. So this is just the graph of y equals 1x, or just y equals x. Now, here's how you're going to change your line. Press left and go over to the line itself. Even in color, Alan, I think you could change color, but it probably defaults to certain colors. But if you go over to this line right here, so see where the cursor is first, press left to go on the equal sign. By the way, you could turn the equation on or off on the graph by highlighting equals or not. So you can leave the equation in, and if you don't want to see it on the graph without having to delete the equation, right now if I graph this, it's only going to graph y1. Even though y2 is loaded, it won't graph it because equals not highlighted. If I hit enter on equals again, it'll automatically do it. So I hit enter down here. So now I press left again. It goes over to the line type, and it's hovering over here now. Press enter to cycle through different types. You have a solid line. You have what looks like shading above. This is good for inequalities when we get there. The next one is shading below. It shades below the line. After that, we've got a line that has little circles along the way, like little every integer. It puts another like tick mark, like a coordinate. It literally graphs coordinates at every integer value. After that, I think we have a dotted line, which is this one. And then I think it's back to, then it's back to like a dash line where you have little spaces in between of them. So try to just play around with these. Pick whichever one you want. I'll pick this one for now and hit graph. On mine, it barely shows it. Let me change mine because it doesn't work that well. This is an old emulator. It might not work as well as yours. Let me use the solid line so you can see the difference. There's y equals 1/2 x, and there's y equals x. See the difference in the thickness of the line? The line that's at y equals x is a much thicker line because I chose that option. Okay, if I didn't choose the thicker line, there are other ones. Actually, you know what? I remember now. One of these has to do, this one's kind of cool. Where is it? This one shows you the beginning of the line as like a projectile, and you watch the line build and move. So watch mine, please. Okay, look at my screen. When I hit graph, watch the second line. See what it does? It's like showing it's like to show you the motion of the graph as it plots every single point along the way with that little mark on it. And it leaves behind like a trail of where the projectile would have moved along that path. If you choose the option without the trail on it, so if I go over again and go down, choose the option without the trail, it'll just be an object moving. So this is just going to be an object. Watch it. That's showing you y equals x without leaving a trail behind. Okay, so if you want to physically show what a projectile moves like, in physics I've used this before, because you can study projectile motion and see the projectile moving across the screen. And that's what that's useful for. Okay, again, the other ones are shading purposes. So if I go down and show you the other ones real quick, this one didn't show anything here. Shade above, where it is? Shade above. I think it's shade above. That's what. Yeah, there it goes. Okay, so there's the line y equals x, and what did it do? It shaded everything above because I turned that feature on shade above. So these are all the different line types here. Now, what are we trying to gain from this problem? Let me go back and just put a thick line or something on. What are we trying to gain? We are trying to gain some knowledge of the impact of slope. So on the third one, let's graph y equals 2x. And on the fourth one, let's graph y equals 4x. We're going to have to change the types of lines we've got. The color feature would be really nice right about now. Because you got 4 colors. I don't think I have 4 types of lines, but let's see what I can do. Maybe I'll make one with a little marker that shows so you can see it. And then the last one, I'll choose that last option even though it really didn't make any difference. Okay, so I have 4 different line types right now. I'm going to hit graph. By the way, are any of your calculators graphing them at the same time? Some of your calculators might be graphing both lines at the same time. You can change that. Depends on which way you want to see it. If you want to see each line appear separately so you can visualize it, it always graphs in order. y1, y2, y3, y4. So you can see them appear one at a time. If they're appearing all at once, here's the feature. Let me show you. It's under mode, right here. If you hit mode, see sequential or simultaneous. This is the graphing mode. If you have it on sequential, it graphs them in sequential order. y1, then it graphs y2, then y3. But if you highlight simultaneously, which is next to the sequential, highlight simultaneous, it'll graph them simultaneously. Yes?
How come you have degree and not radian?
So degree and radian affect your calculator when you get to geometry and trigonometry and you start to measure angles. Angles are normally measured in degrees, like 50 degrees, 60 degrees. You know how we measure distance here in feet and miles, but anywhere else you measure it's meters usually in other countries? Radian is another unit of measurement of angle. So degrees, like 90 degrees, is pi over 2 radians. 180 degrees is pi radians. You're going to learn about that next year and the year after. So for now, you don't have to actually use it at all. It's never going to come up in this class. But when you learn about it in that class, depending on the problem, if it's in degree or radian, the unit, you're going to have the mode correctly chosen. Okay, it's a great question. Guys, these all mean things. This is keeping your answers in scientific notation always here. Floating has to do with how many decimals. If you give it the number 1 or 2, it'll keep it to that precision of decimals. This has to do with regular linear functions. This has to do with parametric equations. You haven't learned about that. Polar equations. You haven't learned about that. I don't even know what the last one is. It's probably sequential something. It means sequential, but I don't even know what it's referring to there. But parametric and polar equations are used in calculus. It has to do with functions of several variables at once. Connected versus dotted. I'm guessing that has to do with the line itself. I've never changed that myself. We'll talk about real and imaginary numbers this year, and we'll see how that's going to change with this one right here. And then the last one I've never actually used. Full horizontal GT, and I've never used it. So I'm going to graph this, and let's take a look at my 4 lines up here. There's y equals 1/2 x, please watch. There's y equals x. Here's y equals 2x. Slowly. And then finally, the last one is y equals 4x. Oh, that actually does make a difference. See it? So, what's happening as the slope number increases? The line gets steeper. Is that obvious to everybody, right? And then the other part of this question that I've asked you here is to graph all of these with negative numbers also. So it's going to get steeper, but in what direction? In the negative or downhill direction. Okay, so go ahead and do the same thing, please. Practice. Go to y equals. Practice inserting a negative sign. Where's the negative sign on the calculator? Where is the negative sign? Isabella?
Like down on the bottom.
Underneath what number?
3.
Underneath the number 3. That is the negative sign. If I use this sign, it's going to give me an error. If I use this to represent negative, it will give me an error. Okay? If I press this in the middle of the calculator when I'm typing stuff in, it'll take my previous answer and subtract something from it. But the negative sign itself is under 3. So let me go over to the parentheses. Let's press insert, and let's insert a negative sign there. Oops, I inserted 2 negative signs. Let me delete one of them. Here, let me insert the negative sign. Second insert, negative. Same thing on the next one. On the number 2, second insert, negative. Go down again on the number 4. Second insert, negative. Finally, graph. Here's y equals negative 1/2 x. Here's y equals negative x. Here's y equals negative 2x. Notice it's getting steeper, but downhill steeper. Right? How many skiers in the room? For downhill skiing, when the ramp gets steeper, you're gaining more velocity. It's like you're going downhill a lot more. So a steeper slope downhill means it's down like that. So this was negative 4, that was negative 2x, negative x, negative 1/2 x. Question? No. Any questions on this concept of slope? Do we understand slope? I hope we really do, because it's kind of been seen in the previous classes at least once, maybe twice now. For you two, you've seen geometry also in addition to your pre-algebra. So it's kind of like beating a dead horse. Okay, we're kind of done with this at this point. It ends on that. This is your homework. Okay, this is not due until Monday, I think. Yeah, because your problem set is due tomorrow. So this is not due until Monday.
We use the test on Monday.
The test is on Monday. Tomorrow's the review. The